Hello! In this video I'll be talking about upstream code quality, how to make open source work out of the box. So first, let's start with a quick introduction. So my name is Guillaume Tucker, I work at Collabora, and in the past few years I've been mostly involved with Kernelci CI, which is about testing the upstream Linux kernel. That comes with many challenges, and as a result of that I've identified a lot of things that I think are common to other open source projects. So this talk is not specifically about Kernelci CI, but obviously it's kind of influenced by the experience I've had while working on it. So let's start from the beginning now. Open source, everybody probably already watching this video already probably knows what open source is. I thought it would be interesting to start from the beginning to explain how, starting from the basic open source concept, we could lead into concepts around how to test the code and how to actually make it really work as a full product. So first of all, open source in 2 words. Open is basically defined by the license that comes with the code, like a GPL license or Mozilla, MIT, BSD. So that tells you can reuse the code and copy it and modify it. And source is basically everything that's covered by the license. So you have code and documentation, and of course you have all metadata like the history from the source control. And one thing you also have typically in an open source project is tests. So this is very important for this talk. We'll keep coming back to that. So what do I mean by out of the box? So what is the box? So first, there's this, the open source exists, there's source code like we've explained, and out of that you want to be able to use the project. So you have a repository that contains all the source code. You have releases that are supposed to be good known versions of the project, and that they include release notes, and then the software can be packaged in a way that can be easy to install. So it could be like pre-compiled or in a format for a Linux distribution or in a Docker image or Flatpak. And then you have documentation that's generated from the source code. So you have like HTML or PDF documentation. So these things you can see that come directly from what's available in the source. However, typically when you get an open source, when you use an open source package out of the box, you don't normally have test results. Although there might be tests, you don't see test results with it. Like in terms of release notes, you can see the changes. You have documentation about the API, so you know how it works. You don't really know what has been tested. Typically, that's not always true, but it's a common pattern that you get the software, you don't really know what has been tested before the release was declared. So I'd like to distinguish open source projects in 2 categories. This is a bit arbitrary, but I think it makes sense in terms of this talk talking about testing. So first you have open source applications. So they are like a complete software product. So they're used directly by users. So the releases are released, they work as is, kind of out of the box. So in this case you have, you can directly install them from the releases, or they're distributed with distributions. And they normally contain fully featured test suites that, according to documentation, the tests are run prior to each release. So I thought it would be interesting to see whether the results are available for this kind of for applications of this kind. So I picked 2 popular ones, like Firefox, a web browser, and Blender for making 3D animations. Actually, there's a talk about Blender at Open Source 101, maybe 2 talks about Blender, so it's a really interesting piece of software, all open source. And actually I haven't found exactly test results, but I've found benchmarks. So there's a website called arewefastyet.com, which is actually, there's a link to that from the Firefox wiki page about testing. So you can see it's actually comparing, it's running benchmarks with Firefox and also with other web browsers to compare the performance between the different web browsers. And then for Blender, there's some benchmarks that show how fast rendering is done with different types of CPUs, different types of GPUs. So these are really useful for users. If you assume that the software is working well, then what you care about is how fast does it work, or compared to other on different platforms compared to other browsers. Still, I haven't found anything about actual functional test results. So there are some bug tracking issues where people report issues, and developers mention the tests passing or failing and trying to fix them and add some tests. So developers are definitely using the test. Like if you want to contribute to Blender, you would need to run tests or add tests for the features you're working on. And there's a release process that's documented for Blender. There's a stabilization period during which only fixes are applied on that branch until the release is declared. And for each release, all the tests apparently have to be passing. That's according to the documentation, but the results are not published anywhere, so we don't really know in which environment the tests have been run, whether there were maybe some known failures or test results that are ignored. We don't know about that. So the only way to find out is run the test yourself, but you don't really know if it's going to be the same environment, so it's hard to compare. Is this an issue or not? I think we'll come back to that in a moment. First, I want to identify what I've observed there. And then second category of open source projects, like I said, the first one is self-contained applications. Another one is open source components. So these are basically things that users don't use directly, but they're like middleware or even lower level, so starting from firmware or Linux kernel or standard C library. So these are building blocks for a full system. So for these, having test results I think would make a lot of sense, because when you integrate that, when you take a component like this and put it in your own product, whether it's in an Linux distribution or a full product, and you want to integrate it in your system, you want to know what kind of test coverage comes with it out of the box, if you want. So I mean, people typically have to run fully integrated tests. So if you make an operating system for a server or for a phone or for any kind of machine, you would basically be testing the whole system. So of course that would be exercising on the components inside. But then if you find a problem, you don't really know if that problem is already covered. If the maintainers knew about it, unless it's in a bug tracking system. So maybe you have to report it. But again, so not having test results is a very common pattern here. There are some cases where you have test results, but it's pretty similar to applications. You don't really see what has been tested as part of an upstream release. So the next step, now we know this, if we go back to the idea of the open source philosophy, where you have one mainline version for the source code, a single code base with many contributors and many use cases, and the mainline is like the intersection of all the different use cases. What is the common ground? So of course the advantage of the open source philosophy is when you make some changes for your own use case, you send them upstream and then they get merged in a mainline version, so that it keeps working with new versions. In principle, at least the code is there, so all the changes will not be breaking your changes. If someone else sends a change, it has to be compatible with what's already there. And maybe your feature will be useful to others. If you have a fix and you send it upstream, that will fix a problem that others might be impacted with as well. So if everybody does that, it reduces the duplication of efforts and it saves time for everyone. So now we have just the open source philosophy focuses on the content of the source code itself. So the question now, knowing that we don't rarely see test results being published, and the open source philosophy is all around getting the source code in one place as if it was just a repository for source code, the question is, so does it work? When you take an open source project, does it actually work? how do you know if it works or not, unless you try it yourself? So this is what I like to call the hidden mass of testing. So you have, in the same way that people talk about downstream changes, say for a product you take, I don't know, Linux kernel for example, and you make many changes to add drivers, add changes, change the APIs and stuff like that. That's your downstream changes. And we know that having too many downstream changes is against the open source philosophy, because then it means it's hard. It means you're not contributing to the main version, and also it means it's going to be harder for you to use a newer version. So I think everybody agrees with that. However, there's also some testing that's done typically with these products, and the results are usually kept within the organization that's been doing the products. So that's what I call the hidden mass of testing. It's like downstream testing that's added value. So everybody has to duplicate these testing efforts, because we don't really know from the basic version that's being taken integrated into a system. We don't really know what the quality is like, so everybody has to redo that to assess the quality within their own systems. So this is kept downstream, and because upstream results are not published, there's no real incentive for people to publish their results either. So now, is it possible to test open source projects? I mean, obviously, yes, there's a lot of different tools already available. So for continuous integration, continuous delivery, you have the main popular ones are GitLab CI, GitHub Actions, Azure Pipelines, and Jenkins, which has been around for a long time. It's very integrated, does a lot of things, but I think some other more modern systems are probably easier to, or more flexible to start with. And Tekton, which is based on Kubernetes, so for running things in cloud clusters. Then then you have frameworks about actually running tests within these environments, like the robot framework or PyTest. I mean, there's a multitude of them depending on your programming language or operating system type. And then there are some automation tools for hardware, so how to start a machine from scratch and load an operating system, interact with it to run some tests and gather the results. So for example, there's Lava, developed by Linaro, or LabGrid, developed by Megatronics, and there's many others. Many people also have created their own. So I don't want to spend too much time looking into all the different things that exist, but I've picked a couple. So we'll start with GitLab CI. So it has a very good tutorial, and it's pretty easy to start. Anybody can create a free account on gitlab.com. So you can create a repository and add a YAML file with a description of the CI you want to run. So every time a merge request is created, or every time a change is pushed to the main branch, a pipeline will be run with the steps you've defined in your YAML file. And of course, you can see that the results are public as well. So you can see the results from the pipeline. Let's take a real world example, the Mesa library. So you can see this is on gitlab.freedesktop.org. So it's a separate instance of GitLab. It's not gitlab.com. That's also something people can do with GitLab. You can install your own instance if you want to. That allows you to configure exactly how you want GitLab to work. And so in this case, so Mesa is basically a library to implement OpenGL and Vulkan for different types of different drivers for different types of GPUs. And it has a CI system called Mesa CI, which is based on GitLab CI. So all the changes going into Mesa normally go through GitLab, so they all have to go through Mesa CI. And if any of the steps fails, then the pipeline will fail, and the changes, the merge request won't be merged. It will block the merge request. That means every test that has been defined in the CI definition has to pass for the changes to be merged. So that's an ideal case, but also as a side effect, as a bonus, you can see the results. Like in the screenshot here, there's only builds, but after that, there's functional tests, and hardware tests as well, running on real platforms, real hardware. And so you can see all the things that have been built and things that have been tested and things that passed and things that failed. So that's an example of where the results are actually available. So if you use the Mesa library, if you pick a version, or even like a snapshot from the main branch or whichever, if you pick any revision, you can see from the GitLab CI what has been tested. So if you want to use a particular GPU, a particular driver, you can see whether tests have actually been run for it. So if a release was made, you can see that within a particular environment with like Docker images to define how the library was built, and the whole environment for a running test is completely defined in the CI, so you know exactly how it was tested. So depending on if you want to use a particular GPU, you can tell whether it's been tested or not. And of course, the added value is if it's not been tested, or if it's not been tested enough, and you find there's some gaps in the coverage, you can add tests, and you can change the CI definition. You can send a merge request to change the CI file, the YAML file, to extend that. So if you find a problem and you fix it, you can send a fix for it, but you can also make sure that the test, you can add a test to avoid regression, for future regression with the same issue, and you can make sure that the test is run by the CI, so no future release would happen if there was that regression again. So here we can start to see the value of upstreaming the tests and publishing the results from Upstream. Let's look at another example. So U-boot is a very common bootloader for typically embedded systems, things like Raspberry Pi, small platforms like this. And it has existed for a long time, and it's still mainly based, the development workflow is still mainly based on emails, like for Linux kernel and some older like classic workflows. However, there's a number of automated testing things that have been put in place. So for example, here there's a GitHub Actions. So the U-boot repository is available on GitHub. I suspect what happens is, well, if you make a pull request, of course, the test will be run. If you send some changes by email, when they get merged, it gets pushed to GitHub, and then some tests will be run there. So the maintainers basically make the checks run. I think it's possible for developers to have checks run as well, but it's not really mandatory to go via GitHub. So that's quite interesting to see how it's kind of a transition from the classic system that maybe some people are used to and want to keep this as part of their workflow, while still trying to enable some benefits of more modern ways of doing software, open source software, including some tests. And in this case, it's using Azure pipelines. So it's running only tests in virtual environments, in containers in the cloud, but still that's a very good starting point. So I don't think it's actually booting U-boot on hardware platforms, but it's doing things with QEMU. Excuse me. And then the third example is Kernelci CI, which is the project I've been working on. So for this one, because the Linux kernel is not just one repository, it's a collection of many repositories from different maintainers, different subsystems, it's really difficult to impose or make the whole community adopt one workflow. So if you want to enable testing, you have to do it for only one tree, or you have to do it on the side, and this is what's going on with Kernelci CI. So it's working kind of in parallel to kernel development. So people send changes to mailing lists, and then they get applied to maintainer branches, and then Kernelci CI will pick that up and build some kernels and run some tests. So because of that, it has a tailored, it's completely tailored CI system. Currently it's using Jenkins, but we're making a newer version with a modular API with a pub subsystem, publisher-subscriber system, to have different tools communicate with each other in a more distributed way. And so it has a web API that you can use to get the data or send some results. It has already distributed test labs. There's maybe about 10 different labs running on hardware. So there's Linaro and ARM and Collabora and Pangatronics and several others as well, running tests on the platforms they care about, and all the results are sent to the main database. There's also tests running in Kubernetes. We're building kernels in Kubernetes, and it has automated bisection feature, which is very useful for kernel because sometimes you have a branch being merged with hundreds or thousands of commits, and before the merge a test may be passing, and after a merge it may be failing, and then you don't really know which commit caused the problem. Because if you look at the pace at which changes go into the Linux kernel, there's about 15,000 changes in each release. That's every 3 months. So that's about one commit every 3 minutes. So if you want it, that's the number of commits being actually merged on average. So if you wanted to do CI, you would have to run tests in 3 minutes. Or even if you do it on a patch series, maybe you would have 15 minutes if the average series is 5 patches. I think it's less than that. So within a few minutes, it's impossible to test whether the kernel still builds for all the architectures and whether all the tests are working. So you can't really do that. You have to do it on less often. And if you do it less often, you test a bigger set of changes. And then so this is the kind of issue we're seeing with an Linux kernel, that you don't see whether other projects have other constraints. So this is why there's so many different CI tools available. You have to be able to choose which ones work best for what you have. And also Kernelci is a KCIDB database, stands for Kernelci database, and that's it's a superset database. So it has all the results shown here, but also it agglomerates results from other CI systems that test the Linux kernel. So we get results from Red Hat, from Google Sysbot, from Intel 0-day, I believe, and from Gen 2, from ARM and Linaro. So the idea is to try to have a full picture over all the tests that are being run on the Linux kernel, on the Upstream Linux kernel. Mostly on the Upstream Linux kernel. There might be some Android ones as well. So that was an example of all the things that exist. So with Linux kernel, you can see the results are available by Kernelci and other systems that test it, but they're not really part of kernel releases. If you take a stable release, you just know you have documentation in the code that's generated in HTML. There's some bug tracking systems in some cases, but you still basically have the code. You don't really know whether it's been tested, whether it's going to work or not. So you have to do that work downstream, and everybody has to replicate it. So going further, how to bridge the gap between the situation where open source only guarantees just to have open code, to having a situation where you can actually use them, where you have some quality control and some kind of guarantee that the code you get is actually working. Maybe this comes from initially maybe a lot of open source projects were like best effort projects. Maybe there was lots of hobbyists working on some things, and so it wasn't really used in the industry, so it didn't really matter too much whether there was quality control or not for it. But now, that's probably still the case with a few projects, but there's so many mainstream projects that are used everywhere, like the Linux kernel and the GNU standard C library or GCC, and not to mention applications like Firefox and Blender and many others. So these are really like professional level quality software. And of course, it's not like mission critical software where, of course, you would need to meet some regulations, some standards, and be really precise about the implications of how safe the software is. There might be some mission critical open source projects, but it's not a typical thing. Still, there's commercial products using open source, and as part of the quality control of the product, knowing the coverage, knowing the quality of the open source components when you take them would be very valuable, in the same way that when you build some a hardware product, you want to know the characteristics of each hardware component. Like, for a battery, you want to know its lifetime and stuff like that. You basically get some data with it, so you know up to which extent you could use it, under which conditions. So for a lot of cases, you don't have that with open source projects. And to be fair, maybe with proprietary software either. So here's a couple of 2-cent suggestions. Maybe that's something where open source can go further than some proprietary software actually. So adopt CI from the start, like I've shown. There's GitLab CI, GitHub Actions, and many other things you can use for free, or if it's for a commercial application, there's plenty of options available there. So if you start something from scratch, at least have some basic CI in place. Maybe you don't have a lot of tests, but you can do like coding style checks, linting the source code, or doing something in place so that every time some test is added, people will systematically add it to the CI as well. And then gate releases on passing tests. So make sure that you use the tools available to only allow changes to be merged if they pass the test. And then following an open testing philosophy. So if you run some tests, or if you have some hardware available, maybe you can make it available to test the upstream version, like we do for Kernelci, where people have test labs that are available to the project, so people can run their own things, but they provide an API token to have access to the test lab from Kernelci. So that's a way of sharing. So sharing the platforms, but also sharing the tests. So if you have some tests, you can upstream the tests at the same time as you upstream fixes or new features. And also upstream the changes in the CI setup so that the tests will actually be run. And also provide test results with releases. That's a great incentive for people to run the test and add tests if the results are published. So that's 2 cents. So here's probably a few questions. So I was hoping this talk would have Q&A at the end, but because it's recorded, it's a bit static. So feel free still to send questions, or I've put my email on the first slide at gtalk@collabora.com. I'm also on IRC, gtalk, and I don't know if there's going to be comments on GitHub, on YouTube. Actually, on GitHub is also a good way of discussing things. You can open GitHub discussions. But here's a couple of, or 3 questions I thought might be relevant here. So open source relies on licenses. So how about tests? Maybe we should have standards for tests, for the test results. So in the same way that many other components, when you build a product, have standards, they have to comply with regulations and standard ways of providing this information. Maybe we could have something like this to harmonize how open source projects share the test results, or can deliver the test results with releases. And then as a side effect of that, maybe should releases be tested by an independent third party? Maybe this is going a bit too far. Maybe this is more like for mission critical software. But still, I think there's maybe some good intention in that. So maybe if it's a machine like a CI system that's not biased like a person. So if someone is running some test and they see there's some warning or something, they think, oh, that's not important, and forget about it or ignore it and make the release happen anyway. If you make a machine, if you rely on a machine to run the tests systematically, and you say we don't tolerate warnings, we don't tolerate any errors, then it will block the release. And then maybe someone will be able to override it by hand, but at least it takes some effort, and it will act a bit like a third-party bot, if you want, robots. Then it could be done for the open source projects that you care about in particular. So in your own work, in your own hobbies, or anything, student projects, maybe you're working on some open source, and are there tests for it? Are they being run? are the releases coming with some quality control, some level of test coverage with results about what has been tested, and so forth. And then going even further, this is more like a pie-in-the-sky idea about an open testing standard. Again, this might be going a bit too far, but I think it's interesting as kind of brainstorming activity to think about, if we wanted to do that, what would it take, and what value would it bring? So if we wanted to create an open, it would have to be an open standard, of course, an open standard for conveying certified test results. So something that when you if you create, say, an operating system image, if every package, every component, when you installed it, maybe you can install binaries, and if it came with test results in a particular format, you could gather all the results from all these packages and have a summary of the whole coverage. A bit like you have tools to collect licensing information, so it will tell you how many packages are GPL and which ones are different MIT or different licenses, so that legal people could make sure that the operating system image can be distributed in particular cases, or that the licenses are respected. And then from a quality control point of view, you could see being able to gather all the results means you already know the baseline of tests, the baseline of coverage, what that coverage is, just by importing the projects into your system. So I've looked at existing examples, maybe. So there's for graphics API from the Kernelci group, like OpenGL and Vulkan. So these are API conformance. Basically, there's an API, and there's a conformance test for drivers. So if a driver says, I'm implementing Vulkan or OpenGL, they can run the conformance test and have the results certified by the Kernelci group to prove that they are compatible with the API. So then, if you have applications that use the API, in principle, you know that the application will work with your driver because your driver is certified to be compliant with the API. So this is very specific to APIs. For functional tests, it would be very, depending on the application, it would be, depending on the project, it could be very different. So I think the standard would be more about the format, like the transport mechanism, rather than the actual definition of the test themselves. So like trying to guarantee that the environment is entirely described, and then if you try to reproduce it, it would have checks to verify that it's the same environment as the reference one. And then having, of course, a standard format for the results, things to verify the integrity of the results using cryptography maybe. And maybe guidelines for the workflow, like you have some ISO standards. Well, these are not really open standards, but you have standards about how to do quality control, how to do processes in many kinds of industries. So the standard could also imply this kind of thing to enforce. If you want to be compliant to the standard, you would have to for example, have a system like GitLab CI in place. So if you could prove that you have that, and that it fits with all the criteria, that would be like ticking one aspect to be compliant. So that's just an idea, a bunch of ideas. I think it's. I don't see a lot of discussion around that. Maybe there are some. Maybe they're kind of offline. I don't see them too much. I thought it would be interesting to bring up. So thank you for watching, and hopefully next time we'll be able to have a live video, or maybe face-to-face. Unfortunately, there were some technical issues with Open Source 101 this time, but it's meet again. So I've just put a slide with some photo credits at the end because I'm using Open Creative Commons images. Thank you for watching.